Hello, everyone. I am honored to introduce our next speaker, Dr. Anne Ongren. She's an applied mathematician and a senior scientist and the department head of applied mathematics at Berkeley Lab. Her primary research interests are computational algorithms for solving partial differential equations for fluid dynamics in various application areas. In 2015, she was named a Society for Industrial and Applied Mathematics SIAM Fellow. She also serves as the Deputy Director of the Department of Energy's Exascale Computing Project, AMREX Co-Design Center, and is a member of multiple ECP teams, including the ExaWind project, which is her topic of discussion today. Please join me in welcoming Anne Ongren. Thank you.
So I want to start by saying I know several people in ESnet. My office is down a flight and over there. And I feel like today I finally have an inkling of what you do. So, to echo a couple meta comments, one of the greatest tributes I can give to ESnet is I never really thought about it. Because I'm one of those scientists that wants to do science and doesn't really think about the infrastructure. I actually work in software infrastructure, so I know what it's like to go under, unseen and unrecognized. But it really is a tribute to ESnet that people like me have been able to take it for granted. So on behalf of all the people like me who take you for granted, thank you. So in the nature of a historic, and this is now, so we've transitioned to the science talks. I'm not going to talk about networking. I probably won't say byte other than I just did. So a little bit different perspective. The title of my talk, let's see, I guess. There we go. So the title of my talk is ExaWind and ESnet. ExaWind here refers to two things. It is the project name of a project that is part of the much larger exascale computing project. It's also the name of a code suite, and aspects of that are funded by the DOE Wind Energy Technologies Office. And so I want to acknowledge both the exascale computing project and the EERE Wind Energy Technologies Office. So a little bit of retrospect, well, looking back a little bit here, not trying to step back. So the question is, when did we first start using wind energy? And of course, you have to define using wind energy. There were sails and sailboats a long time ago. There were windmills pretty far back. So at least 1,000 years, there's evidence that people used windmills to, and of course, they were using mechanical power. There was no electricity. So they were using them to do things like pump water and grind grains, basically. 1850 is significant. It was the first US wind engine company. So somebody decided this was a good idea. There were something like 15 different turbines showcased at the Chicago World's Fair in 1893. It wasn't until 1941, that was the first time that a wind turbine in the US was used to feed into the electrical, well, what was the electrical grid, and it actually powered homes. So 1941 in a place called Grandpa's Knob, Vermont. And one of the questions I'm going to talk about is, how do you decide where to put these? And if you're in Vermont, you happen to know that there are local high spots and low spots, and it's windier on the high spots, as anybody who's hiked in the White Mountains or the Green Mountains. So they put it on top of a knob. But one of the other constraints is you have to be able to get all the parts there. And so one of the reasons they put it there is there was a road that could get them there. It was a relatively short road. It was a peak. So got the name of it, but anyway, Grandpa's Knob in 1941. Now, of course, we come to 2022, and if you live in the Bay Area, you drive past the Altamont Pass, windmills or wind turbines are something that you're very used to seeing. So in 2021, about 9%, over 9% of the US total electricity generation was with wind power. Wind power surpassed hydroelectric in, I believe, 2019. So again, relatively recent. And again, in 2021, the capability was about 136,000 megawatts. So keep in mind, that's about 1/7 of a gigawatt. Okay. One of the things that I want to convince you today is that this is a really exciting time to be working in wind energy. And if you look at this historical past, you say, well, what's changing? Well, what's changing is the advent of offshore. And so, we were talking about 1,000 years ago, 100 years ago. The first offshore wind farm was in 1991. So Vindeby was a Danish wind farm. It's since been decommissioned, but that's really only about 30 years ago. First US offshore wind farm, it's called Deepwater Wind, it's off the coast of Rhode Island, 2016. So that's 6 years ago. First floating wind farm, Scotland, 2017. Now, the thing that you'll see that's missing there, which I wanted to make sure, when's the first US offshore floating wind farm. Hasn't happened yet. So about a month ago in September, they announced the floating offshore wind Earthshot. And so this is a new push. And so when I say it's an exciting time to be working in wind energy, this is why. Things are changing, they're changing fast, and there's a huge opportunity here. So the federal government has mandated 30 gigawatts of new offshore wind energy by 2030. So remember, we had about 1/7 of a gigawatt. 2021, this is now over about 220 times as much. And in fact, in addition, the Earthshot is targeting 15 gigawatts of floating offshore wind capability. So why is this different? So most of the 2030 goal was fixed bottom. Why is floating such a big deal? Well, especially if you live in California and you look at what happens to the bottom of the ocean as you go offshore. On the East Coast, you've got a kind of a ramping area. So there's places to put your wind farms. Off the coast of California, not so much. So floating is really a necessity here. And again, it's just been announced as one of the Earthshots. There are various trade-offs to offshore versus onshore. There are societal impacts, there are environmental impacts, there are a number of things. So today, I'm not going to argue pro or con with those. I just want to talk about the science, because that's what we're working on. Okay. So one of the things that I didn't fully appreciate when I first started looking at wind energy, and again, I'm involved in this ExaWind project that is about modeling wind turbines, is just how big they are. So this one, Windfloat Atlantic, is off the coast of Portugal. The blades on these have these three 8.4 megawatt blades. The blades are 82 meters long. So these are big. Typically, when we think of these wind turbines, we think of the top part, right? We think of the rotor, we have the hub, and we have these blades, and they're really kind of beautiful as they spin out there in the blue sky. But there's this other part, and one of the things that was significant about this one is it was the first, the semi-submersible base. So here's a picture of the base that they're going to load onto a boat and take out there. So these floating platforms, they're 30 meters high. Most of that's going to be submerged, and 50 meters side on that triangle. So these are very, very large objects, which means the designs that worked for the smaller windmills originally and the smaller wind turbines don't necessarily scale up. Let's try that again. And they're only getting bigger. Okay, so if you look back there, you're about 0.2 megawatt. You can tell when you go from between US sources and European sources, we go between meters and feet. So this one's now in feet. But if you look at the land-based wind, there's a time axis on the bottom there. We're between now 2016 and 2035. And you can see these things are just getting bigger. So there's a huge opportunity, but there are a number of challenges. Okay, why is bigger better? So if you look at the power formula for wind turbines, it scales with the area that's swept out by the blades. So longer blades, you get a squared factor, pi r squared, size of a circle. The other thing that happens is the power output scales with the cube of the velocity. Okay, and one of the things that typically happens is there's a frictional effect as wind goes past the ground. If you put a windmill or wind turbine very close to the ground, you have a slower wind speed. Typically, on average, as you go higher, you get faster winds. And so with that cube factor, if you double the winds, you've got 8 times the power output. So we want to maximize the output per turbine. And one way of doing it is making them bigger and taller. Okay, so hopefully I've convinced you this is kind of a big problem. Okay. Sorry. All right, so what are the questions? So I'm actually in the business of research, not design, but the ultimate goal of the research is really to be able to deploy efficient wind turbines. Okay, this is a picture of the Altamont that those of us who drive past there know very well. So to design the next generation of wind farms, there are questions we need to answer. We'll see how fast these appear. So one of the big questions is, where do you put it, right? And you've seen videos. There are wind turbines on ridges, on peaks. There are wind turbines in valleys. There are wind turbines in the ocean. So to understand where to put it, you have to understand the characteristics of the flow in the location where you want to put it. So that's obviously a very important question. That's the Altamont Pass. The size and shape of the blades. There's a whole engineering problem associated with these shapes. We know how much money companies like Boeing have put into wing design. So the shape of these individual turbine blades has changed dramatically in the last 30 years. That's a big question, not one I'm going to answer here. Okay, how many turbines and in what configuration? Sometimes you'll see them stretched out in a line. Sometimes you'll see them in kind of a grid pattern. What determines that? Well, we're going to talk about that. And how many turbines there's something like 4,930 turbines at the Altamont Pass. Another question that I'm not going to answer, but it's very important, is once you have this in place, how do you control this? There are a lot of variables. There are a lot of ways to optimize the power output. This is a big problem. And then finally, something that's come up even more recently, we're all aware of recent weather events and more of a focus on this becoming our new norm. If you're going to build these wind turbines and you're going to put them out in the ocean, you'd like to know that the first hurricane that comes along isn't going to take them out. So that is an increasing question of interest. This is Fiona, by the way, who went right up the East Coast, as we know. Okay, so there are two ways to answer these questions. And this is common in science: data. Data. Let's go out and measure. If we want to put a wind farm somewhere, let's go out and measure. Okay, when somebody first told me about buoys, I pictured the little things that you drop in the water so that a sailboat knows which way to go. No. This is what they call a buoy. And so they put these out in the ocean to measure things like wind speeds and the characteristics of the air. So data is being collected. There's a lot of work being done to collect data at different sites to be able to profile what the wind patterns look like there. So collecting the data, it's time consuming, it's expensive, and even more important in some sense, it doesn't give us the full story. And anybody who works in experiment knows this, that if you imagine that you can sort of see this as an idealized wind farm there, you might space these buoys out, they're expensive, so you don't have that many of them. Maybe you space them out every couple kilometers, and maybe within the wind farm, you space them out every kilometer, maybe outside the wind farm every 10 kilometers. You have data at those points, you have zero data in between those points. And so that's one of those differences. Data, to me, data is truth, right? Assuming we've got the right kind of instruments we're interpreting, that's truth. Nature is doing its thing, we're observing it, but we don't have the in-between values. And so, there we go. And so people like me look to the answer through modeling and simulation. So what I mean here by modeling and simulation is computer models that we take we try to figure out what are the most important processes. We write computer codes, we discretize these, we run them on computers, and we ask, what's the wind doing? And one of the things that I'm hoping to come across, if this is a simulation of 4 wind turbines, there's a lot of simulation data there. We've filled in all the pieces. So if we can believe our simulations, we've got a whole lot more information than we do from the data. We absolutely need the data in order to trust our simulations. The other thing that I want to take a moment to comment on is when I gave the example of how we distribute the buoys, maybe every 1 kilometer resolution within the wind farm, every 10 kilometers, that's a variable resolution. So it's what you could imagine that looking down from overhead at the buoys. In the simulation, it's hard to see. When we look at visualizations, we see a picture and you can't really tell what resolution this was run at. It's not so coarse that you're looking and say, there's the individual data point. And this is actually really important in what we're doing. I'm going to talk about this more later. Okay, so this is not an either or, we need both. And as in most scientific enterprises, the data and the simulation together are way more powerful than either by itself. Okay, we were there a minute. Okay, why is this a hard problem? Wind flow over a flat plate, we're pretty good at that. People have been doing fluid flow calculations for a long time. So what makes this problem harder? So one obviously is we have a variable terrain. What are the effects of complex terrain? They can be very benign or they can be very, very dramatic. Offshore, what are the effects of waves and coastal effects? So depending on how far out we're putting the turbines, they still feel the effect of being near the coastline. The waves change something we call the surface roughness that changes the profile of the wind as we look up. So if you get the wind wrong by a factor of 2, again, that's almost an order of magnitude in wind power. How do the turbine wakes impact each other? We'll see that in a minute. And then the bigger question, how does these weather patterns that may be global patterns, how are they going to affect the weather behavior outside the farm that's going to come inside the farm that's going to affect how that individual turbine spins? So these are things that we all want to figure out. I apologize for the delay here. Okay, so this is what we call a multi-scale problem. And that's a word, we throw around the multi-physics, multi-scale, multi-rate. It really is a multi-scale problem. Here I'm going to focus on the length scales. So again, you can see the global scale. That's where these weather patterns are formed. In the work I do, we're not resolving the global patterns, but that's really, if you think about the definition of the problem, we go from global to mesoscale, like the continental US, for example, to individual plant scale, to turbine scale, to blade scale. So if you're going to do predictive simulation, and where by predictive simulation, we do validation by doing a simulation, trying to match existing data. We know what the data was, we try to match it. Predictive simulation means we want to play the game of what if. We want to predict something that didn't happen. We need to validate first, but to do this, we've got to resolve roughly 8 orders of magnitude. And so when I talked about this, when you look at the picture, you don't see what scales the solution is being simulated at. I'm going to try and convince you that that's a very important part of this problem. Okay. And again, I mentioned that this project has been funded both by the Department of Energy Exascale Computing Project and by the Atmosphere to Electrons project that's part of the wind energy technology process. And if you look at the goal of the ExaWind project, to advance the fundamental understanding of the flow physics that govern whole wind plant performance, including wake formation, complex terrain impacts, and turbine-turbine interaction effects. And the challenge problem, which will be solved in the next year, is 40 wind turbines in a 50 square kilometer area. So this is getting pretty darn realistic. Okay. So let's start with a single turbine. That is a 2 megawatt turbine that's sitting at the NREL facility in Colorado. You see here in the red is mesh. There's some gray lines that are a little bit hard to see in the upper. Those are the blades. The red lines tell you how fine a mesh we're putting around those. That's for those that do this stuff. That's an unstructured mesh that fits this very, very tightly to resolve the boundary layer on the edge of the blades. So that's what we have on the inside. And now if you look, you'll realize that that's embedded in what looks like black boxes. So those are, if you're looking from the outside in, those are increasingly fine meshes, which again, when we talk about resolution with the buoys, it might be 1 kilometer apart or 10 kilometers apart. Here we're going from sub-millimeter scale up to meters and tens of meters. And that's what these unfortunately, the way it comes out with the black and gray, we're doing this nesting that's going to span these 8 orders of magnitude. So this is how we resolve one turbine. But of course, the turbine doesn't live in isolation. Okay, next. Can you do next from there? Can you do it next? Oh, there we go. Okay, so this, we actually don't just care about the flow right at the turbine. That's what's spinning. It's going to take it's going to create electricity. But again, we're not solving one turbine in isolation. So that was a zoom in of that turbine blade. What we're seeing here is the wake behind it. And we're graphing the velocity in the plane. So it gives you, you can think of it as vorticity. You can think of it as the pattern, the air that's coming off the tips there. So that's that. And then let's see if we can see. And this is embedded in a much larger simulation. So this is this idea of nesting, of being able to use resolution. It turns out if we tried to run everything at the fine resolution, it doesn't fit on Frontier. And so it doesn't matter whether ESnet can carry the data because we can't generate it. Okay. So this is one turbine. You might say, we nailed it. Okay, I already said that. This is a great quote that people tend to pull out with multiscale, and I love it, so I'm going to read it to you. There are slightly different versions on the internet depending on which one you see. We used to think that if we knew 1, we knew 2, because 1 and 1 are 2. We are finding that we must learn a great deal more about and. And this is true in so many senses, and I will skip the philosophical diatribe, but the power of and. There we go. This is 2. And if you had done 1, you might extrapolate that and said every one is doing the same thing. And what you see here is that the upwind turbine has clear air coming in. Oh, sorry about that. I don't know if we dare try to do this again. Okay, let's try one more time. You can hardly see the second turbine there. It's so caught up in the wake of the first turbine. So if you're designing a wind farm and you're thinking about how far apart to space these, you'd better understand what's going to happen. And this is why we do those simulations. Okay, that was and in practice. All right, so where are we now? So coming back to our global scale, we can resolve the turbine scale, the blade scale, up through let's call the plant, the farm scale or plant scale. And again, in 2023, we're going to do 40 of those. One of the things that we're working on, there are a lot of atmospheric models out there, and it turns out that a lot of them have been around for quite a while. They were not designed to run on exascale computers. We actually happen to be big believers in running on exascale computers. And so we're actually building a new GPU-ready model that will be able to, we can add it to this ExaWind suite, and we'll be able to basically provide the mesoscale input. It's one thing to run one of these in isolation, you can't see a hurricane coming if you're giving it sort of idealized boundary conditions. And so that's a capability that we're developing. Do we really need supercomputers? I think that I've convinced you of that, but that 15 turbine case I just showed you was 11 billion data points. So if you take a snapshot in time, one snapshot, that's 1.4 terabytes. You might argue we don't need ESnet to make a movie, we can just wait for it. But if we're gonna be analyzing the data, then we need to be able to get the data. That's just one snapshot. Okay, so why am I here? Why am I here talking to you about this? Because, and this is something that's been said, I just want to echo it from the perspective of a, not exactly in the trenches, but a scientist in the trenches. So the reality of modern science is very different. So I realized that when Inder put up the history slide that I started doing computing when in the days of ESnet 1. It's different. It's really changed. So our projects are multi-institutional. What that means is our people are distributed geographically. We used to compute on the computer that was in our building. You know, it was downstairs. Yes, I carried punch cards to the computer that was in the next building, but it was all local, right? Now the computers are across the country. We compute on Frontier, we compute at Argonne, we compute at NERSC. People like me don't have to worry about where we compute. It's this idea that there are these seamless resources that I want to spend my time thinking about the problem that needs solving and how we're going to solve it, and not about, ooh, I wonder if I can use that computer because I may never see my data. And we run more than one simulation. I've showed you the one that was sort of the state of the art right now, that two, but we are doing multiple simulations. We're always validating, we're always improving. We generate a lot of data. So I grabbed the ESnet map here. So ExaWind is one of many projects in the ECP. I'm on 6 different ECP projects plus several other projects. The red circles are the locations of the people that I collaborate with, either daily, weekly, or at most monthly. So I'm one of those many thousand DOE scientists. I collaborate with that many people. Now multiply that by the 10,000 or whatever we are. There's a lot of conversation happening. And I love the science as a conversation. That's absolutely true. So I think I've convinced you, big distributed data, big distributed teams, we are the beneficiaries of what you all do. And now just a thank you to everybody. I want to thank the ExaWind team. There's no way I could put all their names here, but they're a fantastic bunch of people who've done this work. To the folks who run the computers, to the folks who run ESnet, to the folks who fund the work that we do, to ESnet, and to all of you who support the science. And thank you for being here.